When it is difficult or somehow impossible to evaluate a definite integral, we apply approximate methods, and that is what we call numerical integration or approximate integration. And some of the methods that we use include the trapezoidal rule, the midpoint or the mid-ordinate rule, and Simpson's rule. All right. This is the first video on numerical integration, and we're going to begin with trapezoidal rule. So just keep watching, watch to the end. Let's dive right in. How to use trapezoidal rule to determine the approximate value of a definite integral. Let a required definite integral be denoted by the integral of y dx from a to b and be represented by the area under the graph of y equal to f of x between the limit x equal to a and x equal to b as shown below. We are trying to understand the geometric interpretation of the trapezoidal rule. That's why I'm showing you all of these. So this is the graph, and this is the graph of y equal to f of x. From x equal to a to x equal to b. The vertical distance from the x-axis upwards is the y-ordinate. So let's label y1, y2, okay, y3, up till yn plus 1, which is the last y-ordinate. Let the range of integration be divided into n equal intervals of width d, such that d is equal to b minus a all over n. D is the width of the interval. Okay. An approximation to the area under the curve may be determined by joining the tops of the ordinates by straight lines, and so each interval becomes a trapezium. Watch. This is definite integral. Okay, so the area under this curve between the x equal to a and x equal to b gives the definite integral, the integral of y dx from a to b. Okay, so if you look at each of these, just take a look at this this figure, just this part of it. To ordinate the width d, okay, this is the width. From here to here is d. From here to here is d. They all have equal width. Each of these shapes looks like a trapezium. Not exactly a trapezium because this is a curve. So an approximation to the area under the curve is obtained by joining the tops of this ordinate by straight lines. So the area of all the trapeziums added together will give us the area under the curve, and that will be equal to the integral of y dx from a to b. You get it? The area of a trapezium is given by half sum of parallel sides times height. Half into the sum of parallel sides times the vertical height. So what we have to do now is to determine the area of each of these trapeziums. Remember, we are trying to determine the trapezoidal rule. Okay. Now, area of a trapezium, like I said, is 1 over 2 into the sum of parallel sides times the vertical height. So each of them will be a trapezium if we connect the tops of this ordinate by a straight line. So we are going to have something like this. You get it? So for example, I'm dealing with this first one. This is y1, this is y2, and this is d. You get it? So the parallel sides are y1 and y2, and this is the vertical height. So this is what I want to do. I'll write the integral from a to b of y dx is approximately equal to the area of the first trapezium. 1 over 2. The parallel sides are y1 plus y2, and the vertical height is always the width. Then plus the area of the next trapezium. 1 over 2, it will now be y2 plus y3 times d. The next one, 1 over 2, y3 plus y4 times d, plus, you get me now, we are good, as much as we have up to the last one, we will have 1 over 2 into yn plus yn plus 1 into d. Don't be confused. If this is yn plus 1, it means that the ordinate before this is yn. This is approximately equal to, what do you observe? D is common to all of them, as well as 1 over 2. So d into 1 over 2 is common, so bring it out. I'll be having y1 plus y2 plus y2 plus y3 plus y, are you following me? This, and this again, y3 plus y4. Of course, y4 is 2 of them, plus we have 2 of them that are yn also, yn plus yn, not done yet, plus the last one, which is yn plus 1. Alright, so this is approximately equal to d into 1/2. So I have y1 plus yn plus 1. Do you know why I'm writing this? Because we have just 1 for each of the first and the y and the last ordinate. So just one term in y1 and one term in yn plus 1. All others are 2. So I'll be having 2y2, 2y3, 2y4. Without even thinking too much, we have 2y5, 2y6, and so on, plus 2yn, based on what we have here, right? So if I use this 1/2 to multiply the entire bracket, what are we going to have? It's approximately equal to d is outside. 1/2 times this is 1/2 into y1 times this also 1/2 into yn plus 1. But if I use 1/2 to multiply each of these ones that have coefficient of 2, the 1/2 will cancel the 2, leaving us with just y2 plus y3 plus y4 plus up to yn. You get it? So this is what I want to write now. Since both of them, the first ordinate and the last ordinate, have a coefficient of 1 over 2, if I bring out the 1 over 2, I'll be writing y1 plus yn plus 1 plus the remaining ordinates. That's y2 plus y3 plus y4 plus yn. So what is the trapezoidal rule? What you observe now is y1 plus yn plus 1, they are the first and the last ordinates respectively. While from y2 up to yn, they are the remaining ordinates. So trapezoidal rule states that, this is the summary of the rule. The integral from a to b of y dx is approximately equal to d is the width, right? Width of the interval. So I'll be writing width of the interval into 1 over 2 times the first and the last ordinates plus the sum of the remaining ordinates. This is the trapezoidal rule. So if I want to perform numerical integration using the trapezoidal rule, this formula is very, very important. All right, let's take this example. Let us evaluate the integral of 3 over 1 plus x squared dx from x equal to 0 to x equal to 2 using the trapezoidal rule. Correct to 3 decimal places, and we are to use 8 intervals. Okay, first of all, let's rewrite that rule again. The integral from a to b of y dx is equal to the width of the sub-intervals into 1/2 of what? Sum of first and last ordinates, right? Sum of first and last ordinates plus the sum of the remaining ordinates. Sum of remaining ordinates. Good. Now, the limit of integration is from x equal to 0 to x equal to 2. D is the width interval to be equal to the upper limit minus the lower limit divided by the number of intervals. That's 2 minus 0 divided by 8. 2 minus 0 is 2 over 8, and that will give me the width of the interval is 0.25. It means that the ordinates are at, if we have 8 intervals, it means that we're going to have 9 ordinates. Yes, check. The lower limit is 0. So 0. Just follow me. Then what I'll do is to add 0.25 to this 0. That's 0.25, right? Add 0.25 to it again. That will be 1 over 2, which is 0.5. Again, that's 0.75. Again, that's 1. Again, that's 1.25. Again, that's 1.5. I hope you're getting me. Again, that will be 1.75. Again, that was 2. So you can see that it started from the lower limit 0 and ended at the upper limit 2, 0 to 2. So the intervals, this is one interval, another interval, that's 1, 2, 3, 4, 5, 6. Then between this and this 7, between this and this 8 intervals. Then 1, 2, 3, 4, 5, 6, 7, 8, 9 ordinates. I hope you understand what's going on. Okay, so this is what we're going to do now. I'm going to form a table and write my x here. Okay, and then I'll be writing the function itself. So here I'll be writing, in this column I'll write each of these ordinates. 0, this is 0, okay, sorry, this is 0, 0.0, pardon, and this is 0.25, we have 0.5, we have 0.75, okay, we have 1, we have 1.25, we have 1.5, we have 1.75, and we have the last one, which is 2.0. So what we have to do now is to plug in x, is to plug in each of these values for x here and simplify. So for example, this I'm going to set up that computation on my calculator. So I have 3 divided by, I'm going to open a bracket, 1 plus, let's start with the first one, 0 squared. And that's 3. So here I'll be writing 3. Now I will change this 0 to 0.25, okay? So I will be getting 2.823529 and so on and so forth. The question asked us to solve this to 3 decimal places. But meanwhile, I want to leave these values here to 5 decimal places. So 2.82353, 82353 to 5 decimal places. So I'm writing 2.82353 here. So if I change that to 0.5, I'll be getting 2.4. So if I do the same for all others, what this actually means is that if I should draw a graph, okay, let's say this is the curve, this is the function, and this is the curve function, for example. Then we have the y-ordinate, and so on. It is from 0 to what? To 2. It will be 0, it will be 2. This point will be 0.25 here, 0.25. This point will be 0.5, and so on and so forth until I get to 2. You know, this is just a rough sketch. Okay, so each of these values you are seeing here, they are the distance from this x-axis to this point on the curve. So from here to here is 3. From here to here is 2.823353. From here to here is this, and so on and so forth. Now we've done this, then we have just one more thing to do. We now apply the rule. The integral from 0 to 2 of 3 divided by 1 plus x squared dx is approximately equal to, using the trapezoidal rule, we are saying width of interval, which is actually 0.25. Okay, let me write 0.25 into 1 over 2 times sum of the first and last ordinates. Okay, so I am adding the y-ordinate here, not the x-ordinate. Take note. So the first ordinate for y is 3, and the last ordinate for y is 0.6. Then I'm going to add all others. That's from here to here. This is from the second to the 7th, right? Yes. So we're writing 2.82353 plus, this is kind of stressful, 2.4 plus 1.92 is, I'm tired, pardon me, but I hope you understand what I'm saying. So I'm adding up from here to here. Let me just write, okay, dot 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 plus this to show that this is where it ends. 73846. This integral is approximately equal to 0.25 into 3 plus 0.6 actually is 3.6. So divided by these two, that's 1.8. Then let's add up all these together. That's from here to here. 11.4758. So this plus this actually is 13.2758. So I'm having 0.25 times 13.2758. So this one will give me, if I multiply this by this, I'm going to get 3.31895. 3.31895. So we are to approximate to 3 decimal places. So this is approximately equal to 3 points. I will stop here. That will be 3.319. 3.319 to 3 decimal places. So this integral to 3 decimal places is approximately this. Using the trapezoidal rule, let us determine the integral from 0 to pi over 3 of the square root of sine theta d theta. and here we are making use of 6 intervals, and that means that the width of each subinterval is pi over 3 minus 0, which is this minus this, divided by that 6, and that will be pi over 18 in radians. Okay, when dealing with problems like this, the value is always in radians. Okay, so I will leave it in radians. So I'm going to set my calculator to radians. You can see it's in radians. So the ordinates are at, we're using 6 intervals, so we're going to have 7 ordinates. 0, the first one. Add pi over 18 to 0, that will be pi over 18 as well. Then add pi over 18 to pi over 18. I think my calculator can do this for me. Let me see. Pi, this is pi. Okay, sorry. Shift pi divided by 18 plus so that is pi over 9, right? So if I add pi over 18 to it again, I'll be getting pi over 6. Add pi over 18 to it again, you're going to get 2 pi over 9. Do same, you're going to get 5 pi over 18. And do same again, you're going to get the last one, which is pi over 3. So the ordinate will be at this point. That's the y ordinate will be at this point on the x-axis. 1, 2, 3, 4, 5, 6, 7. So 7 ordinate 6 intervals. 1, 2, 3, 4, 5, 6. All right. So let me create my table. X, that's 0. I'm writing those ordinates. Pi over 18, pi over 9. All right, this is it. Then I'll be writing the function here, which is the square root of sine theta. So the square root of sine theta. I told you theta is in radians. Now let's begin to evaluate. Okay. So I have this down. The square root of sine, let's start with the first one. My calculator is in radians, so I'm good to go. Sine 0. That's 0. So I'm writing 0 here. Sine pi over 18. Alright, in the question, I didn't state it anyways, but we have to leave this solution to 3 decimal places. Okay, but meanwhile, I want to work with 5 decimal places. That will be 0.41671 to 5 decimal places. So this is, so the next one is pi divided 9. That's 0.58482. And the last one we have pi divided 3. 0.93060 to 5 decimal places. So using the trapezoidal rule, the integral from 0 to pi over 3 of the square root of sine theta d theta is equal to this. The rule says width of subintervals, which is pi over 18 into 1 over 2 times the sum of the first and the last ordinates. That will be 0, the first ordinate, plus this, plus 0.9. Sorry, this is an approximate value. It's approximately equal So this 0.93060 plus the sum of the others, that will be 0.41671 plus 0.58482 plus 0.70711 plus 0.80174 plus the last one. 0.93060 divided by 2 is 0.4653. 0.4653. Adding up the other ordinates, okay, we're going to have 3.38562. Be very, very careful of errors, okay? So we have pi over 18. If you add this and this, that will be 3.85092. So I'm going to say 3.85092 times pi, which is the pi outside, divided by 18, 0.672112, and so on and so forth. So correct to 3 decimal places, this integral is approximately equal to 0.672 to 3 decimal places, okay, to 3 dp. All right, this is the trapezoidal rule at work, and I hope you understand and you like the video. We have other rules such as the Simpson's rule and the mid-ordinate rule. I want to talk about them later, so just keep following, subscribe, like, and share this video to your friends and to your classmates. I'll see you in the next one.